Alright, so today guys I'm going to go through the 2006 free response for the differential equation slope fields question. And this whole packet mainly has slope fields, differential equations, and some related rates, but this one has both slope fields and differential equations. And I would not be surprised if you guys saw a slope field sometime this year because we have not seen one in several years. But typically these are a combo question where it's a slope field plus then a differential equation after it. So we're given this differential equation. They tell us x cannot equal 0. And we want to first sketch a slope field. So start plugging in the points that they give you here. So there's 8 points. Make sure you're only graphing on those 8 points. We have 1, 0. So plug in x is 1, y is 0. You get 1. Plug in 2, you get 1/2. And then plug in 1, 1, we get 2 over 1, which is 2. And again, you don't have to be perfect with these slopes. Just make sure that slope is steeper than the last two you just did. Plug in the next one over here. We got -1, 0. So that'll be a -1 slope. Plug in -2, you get -1/2. Plug in -1, 1, and we get a -2. Now down here, since y is equal to -1, both of these will give us slope is 0, because you'll get 0 over 1, and you'll get 0 over -1. This was worth 2 points. Basically, as long as your slopes looked semi-accurate, you got the full 2 points on it. Now, the second part of the question is a give me, and the fact that you are always going to be given a question like this in some form. It'll either be in a related rate problem, or in a slope field problem, or some other type of real-world problem where you have to find the particular solution to a differential equation given a point. So we're given the point -1, 1 here. That's going to help us find our c value. And make sure you state the domain if they ask you for the domain. So let's go ahead and get started on this one. So we have our differential equation is 1 plus y over x. First step is to separate the variables. You will lose all the points for the problem if you don't separate the variables. And even if you don't know how to take the integer to separate the variables, at least you'll get 1 point. So we get 1 over 1 plus y dy is equal to 1 over x dx. Then you're going to integrate both sides. This side turns to natural log of the absolute value of x. Very important you have that absolute value in there. Don't forget your plus c. As soon as you forget your plus c, you lose 3 points. And then we have natural log of absolute value of y plus 1 over here. Now the hard part, we have to solve for y. So remember, this is a base e log, so it'll be e to the natural log of absolute value of x plus c is equal to, we can lose the absolute value here because this exponential will always be positive, so you don't have to worry about this side not being positive anymore. Now I don't like how this right hand side is written. It's going to be very hard to solve for c later on if we leave it like this, so I'm going to split this up into this. And then e to the c is just some constant, so let's just call it c. And you can actually go a step further with this. This right here, we have the same base for this log and this exponent, so essentially these cancel and you're left with absolute value of x, and then we have times c, and then over here we still have the y plus 1. Solve for y, just subtract the 1 over. And now we can plug in our point to solve for c. Okay, so let's plug in our point. Remember, it was -1, 1, so plug that in. We get 1 is equal to c times the absolute value of -1 minus 1. So add the 1 over, we get 2 is just c. Plug that in, we get y equals 2 absolute value of x minus 1. Now for the domain part of this, because x was negative up here, and because our graph of the slope field stops once you get here, there's basically an asymptote happening there, or a hole in the graph, something like that, and we're using, not that point, we're using this point right here, we have to keep our absolute value graph on this side of the graph. So it has to be for all x's for a domain. Oops, sorry guys, I don't know what happened there. It has to be for all x's less than 0. And that was worth 1 point. Okay, all this work here is worth 6 points for finding your differential equation correctly, and then 1 point for the domain. So even if you got the domain wrong, you got 8 out of the 9 points for this whole problem. All right, now moving on to the 2007, we're going to look at number 5, which is a related rate problem. This is not a differential equation problem. Now, related rates are not a very common topic on there. But again, I would not be surprised. It's been a long time since they put a related rate on there that you walk in there and you see one on that exam. Now this is a no calculator question. They do give us this table. And we're going to have to do stuff with Riemann sums, which again, this is something we just reviewed. This is a very common application that they have in the AP exam. So we're given these values. Keep in mind that this is r prime of t is your dependent variable in here. The volume of a spherical hot air balloon expands as the air inside the balloon is heated. The radius of the balloon in feet is modeled by a twice differentiable function r of time t, where t is measured in minutes. For 0 to 12, the graph of r is concave down. That's a really obscure piece of information they're giving there, so I'm going to underline it. There has to be a reason why they're giving us that. The table above gives selected values of the rate of change r prime of t of the radius of the balloon over the time interval 0 to 12. The radius of the balloon is 30 feet when time equals 5. So they're essentially giving you a very important point there. Now notice how they give you the volume formula. You don't have to have any obscure volume or memorized. They will give those to you, and that's one like that. Alright, so in part A it says estimate the radius of the balloon when time equals 5.4 using a tangent line approximation at t equals 5. Is your estimate greater than or less than the true value? Give a reason for your answer. This is just a linearization question. We're using a line to estimate a curve, so it's the linearization idea. So we have the point. When time is 5, the radius is 30. That was that information they gave us up here. Remember, this is t and this is r. The slope is given to us in the table. If you go back to the table and look at time equals 5, our slope is 2 because that's our derivative. So we have our slope is 2, write your equation. So r minus 30 is equal to our slope times t minus 5. Just make sure you're using t's and r's instead of x's and y's. Add the 30 over, we get r of t is equal to 2 times t minus 5 plus 30. Now we're going to plug in the point we want, which is 5.4. We get 2 times 0.4 plus 30, which is 0.8 plus 30. So 30.8 feet is our estimation.
Similar.
Now, is our estimate greater than or less than the true value? You want to give a reason for your answer. So is it going to be greater than less? And this is where the concave down part of this actually comes into it. So if the graph of this function is concave down the entire time, and we're looking at time equals 5, which let's just suppose it's there, when we draw a tangent line in there, the tangent line is always going to be above. So if I choose 5.4 just to the right of that, it's going to be an overestimate of what the curve is actually getting at. So we would just say that the approximation is an overestimate since r is concave down, and that's the only reason what you have to give. Okay, you don't have to go into any more detail than that, just then say that it's concave down. Part B says find the rate of change the volume of the balloon with respect to time when t equals 5. Indicate units of measure. This is where the related rates part of this comes in. We're looking for dV dt, the change in volume in terms of time. We have dr dt. If you go back to the table they give us, the change in rate of the radius in terms of time at time equals 5 is 2. Our radius is 30, time is 5. Set up your equation. So volume is 4/3 pi r cubed. Take the derivative with respect to time. So dV dt is going to equal 4 pi r squared times derivative radius with respect to time. And now plug everything in. Keep in mind this is no calculator, so if you want to leave it with stuff just plugged in, feel free to, but I'm going to actually figure out what this is. So we have 4 pi times 2 is 8 pi, times 30 squared is 9, and then 2 zeros. Multiply that out, you get 7,200 pi. Make sure you put units, they ask for that, cubic feet per minute, since this is change in volume with respect to time. And there is your related rate questions answer. Now in part C, it says use a right Riemann sum with 5 sum intervals and by the data in the table to approximate this integral. And then what seems to be a very common question using correct units, explain what that means. Okay, so you always will have to explain these. Don't just find the answer, make sure you're explaining what you're finding. So if we're going to do an RRAM to estimate this, let's go back and look at our rectangles. So our first rectangle is going to have a width of 2, and if we're doing an RRAM, it's going to be the right endpoint. So it'll be 2 times 4. Plus the next rectangle has a width of 3, and the right endpoint is that 2 that we've been using a couple times now. Plus now the next rectangle has a width of 2 and a height of 1.2, again using that left or right endpoint. Plus then the next rectangle has a width of 4 and again height of 0.6. And then finally our last rectangle has a width of 1 and a height of 0.5. Now, of course, you can always leave this on no calculator part. I'm actually going to multiply it out because these are not terrible numbers. And then add this up. This is 14. This is 5.3. So you get 19.3 feet is what that integral approximately is equaling to based on your RRAM. Now, it says using correct units, explain what this is. So we're going to say that this integral from 0 to 12 of r prime of t doing. We're taking the integral of a rate, so we're going to get a total out. So what we're going to say is the total change in the radius in feet, don't forget your units, from time equals 0 minutes to time equals 12 minutes. Or you can say in the 12 minutes or in the first 12 minutes. You have to, though, talk about that time interval they give you in there. You can also say it's the total increase, since it's obviously increasing the entire time, so there's many ways you can state that. That's still correct. And finally, in Part D, it says, is your approximation in Part C greater than or less than the actual integral? And give a reason for your answer. Well, my reason for this one is going to be based on whether this is increasing or decreasing. When you're looking at R prime, it's actually increasing the entire time. So since it's increasing the entire time, your RRAM is always underneath the graph. Okay, your right endpoints are always less than your left endpoints. So this is going to be an underestimate. So we would say that our approximation, oh, stop going up now, buddy. All right, so our approximation is an underestimate since, and our reason would be just since R prime is decreasing. You don't have to say anything about the rectangles being underneath the graph. In fact, I encourage you not to say that. The whole point is whether it's increasing or decreasing gives you the correct answer. So that's it, guys. You have to do the two 2008 ones in there. So 2008 number 5, which is no calculator. Again, another slope field differential equation question. And then you also have to do the 2008 number 3, which is calculator okay that year. So you may use your calculator. In fact, you might need it for some of the parts in that. And that's a related rate question. I do encourage you to do the 2012 number 5, although it's not assigned, it's one of those extra practice problems, but they have given a question like that the last 3 years. So I would definitely verse myself in that, not just for the AP exam, but for your next quiz. You know I like to pick at least one extra practice problem to make sure you guys are doing those. Alright, hope you have a good day, guys, and I'll see you later.